All right, welcome to this video. So in this video, I wanted to show, originally I was just going to show the problem number 10, the uh, distribution of multiplication over addition using the left hand. But during last night's expedition, I actually thought it might be useful to have the comparison of the right and the left, and then also um, distributing or showing a connection? I don't know. Like I just feel like the contrast will be helpful to kind of make sense of things. So this is using Peano's axioms. And so we have our five axioms, which I won't write here, but they're easy to identify. I will write the definition of addition. So we will be using these. So addition, the definition of addition is x plus a 0 for x in the natural numbers, and then also x plus the successor of y is equal to the successor of x plus y. Okay, so I'll often refer to this one as a1 and this one as a2 in later in the proofs that follow. Okay, and then likewise, the additional operation, of course, is multiplication, and so multiplication again will be x times 0 is equal to 0. I'll call that one m1, and then of course x times the successor of y is going to equal x times y plus x, and that'll be m2. Okay, so we'll use those definitions for the operation of addition and multiplication. Okay, all right, so squiggle that out. And so for the right multiplication, this one tends to be a little bit easier, primarily because if you notice by our definitions of addition and multiplication, they follow from the right side. In other words, we are sort of, if you think about it, like right distributing here. Okay, so I'm going to first define my set M to equal for all z in the natural numbers, the following set for all x and y in z, in not z, sorry, in n, such that z times x plus y is equal to z times x plus, oh, 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 mixing up. So scratch that. I'm doing, I forgot which one I was doing. I'm doing right first. So for all z and n, then I'm going to do for all x and y in the natural numbers, such that x plus y times z is equal to x times z plus y times z. Okay, so this is my set M, and this is what, using Peano's axiom number 5, the method of induction, mathematical induction, I will show that if I can show the successor of this function, and I'm doing induction on the variable z here, if the successor of z is in M, then it's equal to the entire set of natural numbers. Okay, so it's true for all natural numbers at that point. Okay, so using the method of mathematical induction, I'm going to establish my base case. Okay, here. And so since I'm doing induction on z, then that means that z is equal to 0. That's our first natural number. And we're doing this to show that the set M is not empty. Okay, so letting z equal 0, just plugging that in, then I get x times, or no, sorry, x plus y times 0. Well, what is that? You may be asking yourself, what is this thing? Well, we know by well, we want to show, I guess I should write out the whole thing first. I was kind of thinking about like how I wanted to write this out. I want to show that that is equal to x times 0 plus y times 0. Okay, that's what I'm trying to show. So starting on this side, I can redefine x plus y. I know that this is a natural number. And by axiom M1, this whole side, so if you define, just to kind of see it, x plus y equal to c, then what we have here is c times 0. And this equals 0 by M1. Okay. And then I can define by a by similarly by M1, x dot 0 equals 0 and y dot 0 equals 0. Okay. And so I also know then that by A1 that 0 plus 0 equals 0. And so that concludes the right-hand side is also, oh, I can't see. So the right-hand side here is also, so this is equal to 0 and this is equal to 0. So I'm doing it separately. So I've just shown that this, the right left-hand side, so if you think of this kind of like a line, this is showing the left-hand side is equal to 0. And then, and that's by M1, that's true. Okay, so that kind of goes with that. This is horribly laid out, but hopefully it makes sense. And then here I have x times 0 plus y times 0. So what that's saying is I have 0 plus 0 by M1. That's defined by definition, those are equal to 0. So adding 0 plus 0 by A1 means that I'm adding 0 to both, so it doesn't change anything, so it's still equal to 0. And so I've shown equality on both sides. So this shows then that 0 is in M, which is not equal to the empty set. Okay. All right, so let's go ahead and jump to the induction hypothesis. Okay, so we have the induction hypothesis. Then that says that for all x, y, and z in N, that we're assuming that they're part of the set M. In other words, x plus y times z is going to equal x times z plus y times z. Okay, and so in that case, then that's what we're trying to show, or that's what we're not trying to show, that's what we're trying to assume. And so the induction step then is we want to show then, of course, that x plus y times the successor of z is equal to x times the successor of z plus y times the successor of z. Okay, so we're trying to show that is the case. And if we can show this, that means the successor of z is in the set M, which means then that the set M by the principle of mathematical induction is equal to the set of natural numbers. Okay, so just starting with this side here, it may be helpful to think again of let x plus y equals c, and then you have c times the successor of z. And then by the definition of multiplication M2, we know that this is equal to c times the success, is equal to c times the successor of z. No, sorry, not m by 2. That's just by substitution. And then the successor of z, c times the successor of z by the definition of M2, then of course is equal to c times z plus c. Okay, but remember that c was equal to x plus y, so this is really equal to x plus y times z plus x plus y. That's why I use the letter C there to kind of help, because that can be a little bit confusing if you're losing track of all the different terms. Okay. All right. Now, by the induction, so this is by M2, and then by the induction hypothesis, I can distribute the z's here into each of those terms. So I have x times z plus y times z plus x plus y. And then by the associativity and commutativity of the natural numbers over addition, which I have shown in a previous example, I can rearrange the order here so that this term and this term are grouped together, and then also this term and this term are grouped together. So I can change the order of them and then reassociate them as well. And so I get x times z plus x here, and then plus y times z times, or plus y there. And then by the definition of multiplication, M2, this is just x times the successor of z plus, and then over here I have y times the successor of z, okay, which is exactly what I wanted to show. And so I can then conclude, of course, then that since the successor of z is in M, by the principle of mathematical induction, by principle of mathematical induction, M is equal to the set of natural numbers. Okay, and so we've just shown here then that the right distribution of multiplication over addition exists, and it's true. And so let's then follow to showing it from the left-hand side. Okay, and so this is where the conversation from last night I think really showed its value. It was a um, really nice surprise, I think. Okay, so if we define our set M in the same fashion, right? So if we set M equal to the set of Z in N, such that for all X and Y in Z, keep saying in Z, we have Z times X plus Y is equal to Z times X plus Z times Y. Um, So for this set, the challenge that we get, you can actually see it right away. So if we do induction on Z again here, and we let Z equal 0, then we get 0 times X plus Y. Okay, and we want to show that that's equal to 0 times X plus 0 times Y. And the problem immediately follows. You can go even further, and which is what we did. We did some hand waving to try to show that this is in fact 0 on both cases. But the issue is that multiplication is defined by the right, not by the left distribution. And so what do we have there? Is we have an undefined quantity. In other words, we don't know what this operation is based in our definition, um, and that's the challenge here, especially with respect to the definition of the operation of multiplication and also addition. And so immediately we kind of run into this challenge here. And so instead of trying to reinvent the wheel or trying to figure out how to do it with this situation, really another way to think about this problem is our definition of the set. The definition will be the same, but what we choose to do induction on can change. And in that simple change, then we can utilize then the properties of the operations as defined here. And so here's what I mean by that. So let's not ignore this. Let's take this and go, okay, so it's undefined operation here. So what if we say, okay, let M equal the set such that Y is in the natural numbers, then for all X and Z in the natural numbers, then we want to have that Z times X plus Y is equal to ZX plus Z times Y. Okay. Now you may compare the two and notice that they're exactly the same with one small difference. We're choosing a different variable to do induction on. And by doing so, it's a clever little approach that allows us then to show that the right distribution of multiplication over addition can apply as well. Okay, so if we take this as our set then our base case, since we're doing induction on Y, not on Z this time, we're going to let Y equal 0. And so here, watch how this plays out. We get Z times X plus 0. And we want to show that that's equal to Z times X plus Z times 0. Okay, so we want to show that that's true. I'm not saying this is true. We want to show that this is true. Okay. All right, so let's do that. So Z times X plus 0. Well, what is that? By A1, see how we can use this now? By A1, then this is just Z times X. That's an X. This is just Z times X. Okay. And then that doesn't quite look like this, but I also know, so that's by A1, but I also can note that Z times 0 is equal to 0 by M1, and uh, 0, Z times 0 plus 0 is equal to 0 by A1. Yeah, by A1. Yeah. Okay. So, or well, anything here plus 0 is equal to 0. So if I take Z times X and I add 0 to it, that doesn't change anything. So ZX plus 0. So I'm just taking this side right here and saying, oh, okay, well then zx is the same thing as zx plus 0. Okay, so this implies that zx plus 0 is still 0, which is then equal to, and that's by a1. Okay, so this is by a1. By a1. Okay, but this 0 is the same thing as z times 0. So this is z times x plus z times 0. And this is by m1. Okay, and now if you look, that's exactly what we wanted to show. Okay, so 0 is in m, and so that's not equal to the empty set. And so we've got excellent. All right, so now we have the base case established. So let's then take up the induction hypothesis here. All right, so the induction hypothesis in this case, of course, is that for all x, y, and z in n, all the natural numbers, what we want to assume is that z times x plus y is equal to z times x plus z times y. And then the induction step, what we want to show is that that the z times x plus the successor of y is equal to z times x plus z times the successor of y. Okay, so that's what we want to show. All right. So this then, in our previous issue, remember with the challenges of the right distribution, that was the issue because we didn't have multiplication defined on the right-hand side. However, we can use a2 here. That's going to come in handy here. So we have something of this form, and we're going to write it like this. Okay, so I can rewrite. So let's start on the left-hand side here. So we have z times x plus the successor of y. Okay, now by a2, I can write this as z times the successor of x plus y. That's by a2. Okay, and then by the definition of multiplication, so it may help to think of this as like c. So you can write this as z times the successor of c, if it helps like that, and then think of it in that form. Okay, and then that is for m2. This is x times the successor of c. So what do we have? What we have is z times c plus z. Okay, and that's by m2. Okay, all right, and then remember c was x plus y, of course, and that was plus z. Okay, so that's just resubstituting, and then by the induction hypothesis, then of course I can write this as z times x plus z times y plus z by the induction hypothesis. Okay, and then by associativity of addition, I can look at this term specifically and recognize that that is z times x. This is plus. This is the z times the successor of y by m2. Okay, and now if you look at what we have here, this is exactly what we wanted to show originally. Okay, so that means that the successor of y is in m. Okay, and by that definition, then of course, since the successor of y, so this implies the successor of y is in m. Okay, so by principle of mathematical induction, then we have that m is actually equal to the whole set of natural numbers. Okay, and that is then showing us that the distribution of multiplication over addition from the right also is true. All right, and so that was a really nice complement to the original attempt where we were following the same, let's see, what was it? Where we were following a similar set that we had done with the left distribution, but we ran into the error that the definition of the operation that we had no longer worked. Now, there's another way to do this, which for the length of this video, I will omit, but I think that sums up a really nice approach or looking at the two forms of the distributive law using Peano's axioms and the definition of multiplication and division. Okay. All right. I hope that was helpful, and I will see you in the next video.